Hi, it's Professor Cummings. I have another example problem for kinematics, looking at rotations. So let's go ahead and get started. You've got the motor shown, the motor being this little unit here up at the top with A. The motor shown turns a wheel attached to a blower. Right? And if the pulley A connected to that motor begins to rotate from rest with a constant angular acceleration of alpha sub A equals to 2 radians per second squared. Determine the magnitudes of the velocity and the acceleration of point P, down here, on the wheel after the pulley is turned 2 revolutions. All right. Assume the transmission belt does not slip on the pulley on the wheel. And again, whenever they say the pulley, they're up here. Whenever they say the wheel, here. So we're looking at the pulley is turned 2 revolutions. And we're going to assume that that transmission belt doesn't slip. So there's not a bunch of jerking and not a lot of wasted energy. Again, we've got an angular acceleration. We know that is constant. That means we can use our 4 kinematic equations. And we're really concerned with what's going on up here, dictating what's going down on this wheel. So when we take this problem, we're going to lay it out, see what we have given. We've got our angular acceleration up here of A. We got the radius of A at 0.15 meters and the radius of B of 0.4 meters. So again, considering they're connected by that transmission belt, we know that that tangential velocity and acceleration will be constant between those two. So the thing that's going to change is going to be based around these radii, right? The radius of the two. So the tangentials are going to be different, the tangentials are going to be the same, even though the angulars are going to be different based around those radii. So also we got this little note here, the angular velocity starts from rest, so everything is going to be starting from a point of 0, and then we're going to have this constant acceleration. So that dictates the kind of equations that we're going to use, how we're going to approach this problem. Let's go ahead and set up our solution. Alrighty, so the first thing we have to do is we have to start converting everything into radians. So revolutions to radians. So they told us 2 revolutions on this pulley up here at A. So let's go ahead and make that into radians. So we got, it says 2 revolutions, going to be the full travel up here before we find out what's going on with P. So theta sub A is going to be 2 revolutions, and the conversion is, you got 2 pi radians, for every revolution. So you're going to put 12.57 radians that we're looking at for that first pulley. So now we can start doing our calculations based around that. All right. So again, now we've got our kinematic equations. We've got our, or we're trying to find an angular velocity. Or we can go easily and get our angular velocity based off this, what information we have, because we got angular acceleration. We've got a difference in theta. So we got a starting point of 0, and we've got a final point of 12.75 radian. So that's how much that pulley is going to travel. So we have our kinematic equation that looks at the difference between the 2 thetas, the ending and beginning theta. And based on that constant acceleration, we should be able to find a beginning and an ending angular velocity, considering our angular velocity is 0. So here we have it. Let me go ahead and make this a pen, just so I can demonstrate a few things. So this is our final angular velocity squared on pulley A. And this is our initial, because we know it's coming from rest, plus 2A sub C. A is just saying that that's constant. And we got our difference in our travel. So starting from rest, starting from rest, initial, and going to our final. So we can just go ahead and start taking what's going to just fall out because it's starting from rest. So initially this is going to go away. It doesn't have, if it's starting from rest, it doesn't have an angular velocity. And if it's starting from rest, that means its starting point, we're just going to call it 0. So those 2 come out as 0, and 2 times the constant angular acceleration, 2 radians per second, that was given. And we found our final destination, our final point of concern is 12.57 radians. So multiply those together, that's 4 times 12.57. and then take the square root of that, you end up with 7.09 radians per second. So this is the final angular velocity on this pulley up here. All right, that's our final for the pulley up at the top. Now, the tangential velocity of the pulley and the wheel are equal. You know, they've got the same tangential velocity based on this belt. So the tangential velocity is going to be the same, even though our angular velocities are going to be different based on the two radii. And we're going to have that equation that's going to show this. So if you remember that equation, our tangential velocity is equal to omega, our angular velocity, times the radius of A, which is the same as our angular velocity of B times our radius of B. You know, so again, we've got and these are what's known. We know our angular velocity. We know both of our radius, so we can just divide both sides by the radius of B, and we're left with our angular velocity. So divide both sides by the radius of B, that 0.4. You know, omega A times r sub A divided by r sub B, and what you end up with cancels our meters. So what you're left here with is going to be the units wise radians per second, right? So to multiply by 0.15 divided by 0.4, and we are left with an angular velocity on this wheel of 2.659 radians per second. Right. So now we have that. You know, we have that angular velocity. We even have if we wanted to, we can calculate a tangential velocity on both of those. On that wheel. You know, what we're ultimately trying to find, you know, are the magnitudes of the velocity and acceleration of point P. So let's go ahead and start off and look at the acceleration. So again, now we got our acceleration. We have this equation we can use. So the tangential acceleration, you know, again, around this wheel, the tangential acceleration is the angular acceleration of A times r sub A is equal to the angular acceleration of B times r sub B. Like I said, there's a constant, because of that belt, there's a constant tangential acceleration between the two. So one thing we knew right off the bat. And since we know this was given, and both of those were given in the beginning, we can solve for A sub B, or A sub T, and or A sub B, which is the same way we did for angular velocity. Again, based around the radius, those two go away, and we end up with an angular acceleration of B at 0.750 radians per second squared. So now we've got information on angular velocity and acceleration. Angular velocity and acceleration for B. So the wheel is the thing we were really concerned with. So that was the concern with here. Point P on that wheel. So now we have enough information to go back and start kind of getting down to our point of interest. All right. So here we have it. I just block those on because that's really what we're going to need to turn those into tangentials, or excuse me, into the magnitude. All right. So now let's look at what's going on with point P, because a few things are going to be different because it's got a bigger radius. So the point P on that wheel. All right. So let's think about what's going on with that, because we've got the radius, we've got two different angular accelerations. We're going to be making a lot of conversions, calculating a lot of conversions here based around point P. So the first thing with point P, we need the tangential velocity when they're talking about the magnitude. Tangential velocity of point P, which is just basically that same equation, angular velocity of point B, or of wheel B times radius of B. It's 2.659 times that radius of 0.4 meters. It was 1.04 meters per second. Our tangential when we think about acceleration, we're looking at the magnitude of acceleration. So we're going to have to do this a little bit different. We need the tangential and we need the normal, right? So we've got point P, and we're looking at that tangential acceleration of P, and we're looking at the normal acceleration of P, right? So tangential and normal. We've got two different equations for this. So tangential is very similar to our angular velocity. So we got an angular acceleration, tangential velocity. Our angular acceleration of point B, or pulley B, times r sub b. Just multiply those together, 0.750 radians per second squared times the same radius gives us 0.3 meters per second squared. And we look at our normal, we have a different equation. We need to have that angular velocity squared times that radius. And we have both of those. So 2.659 radians per second. That should be just radians per second here. Radians per second. And the quantity squared times the radius, which gets us 2.827 meters per second squared. So we have a tangential and we've got a normal. So what we need to do is find the resultant of those two, and that will get us our magnitude. And all we need is the root sum squared. So this is the magnitude of point P, the acceleration. So we have the square root of 0.3 meters per second squared plus 2.827 meters per second squared, the quantity squared. So the square of both of those from up here. So the square of both of those, and then take the square root of that. What we end up with is the magnitude is 2.84 meters per second squared. So there's the magnitude of both the velocity of point P on the big wheel and the acceleration of point P on the wheel. Now, again, all this was based around a couple of things that I want you to take with you on this problem. So we had the information based around one wheel, and we had a transmission belt between that. And, we had all of our equations, but the concept that you should take away is how that tangential velocity was the our tangential velocity and acceleration were the connecting factor between the two wheels. So you know the equations that make that connection, and you can solve that problem. Again, this is Professor Cummings, and I will talk to you soon.